Hello and welcome to today's session. At the end of this session, you will have a deep understanding on all the main concepts and a great big picture overview of how AWS ECS or Elastic Container Service works. I have made this course to cover the theoretical concepts. If you want me to cover the hands-on aspect, please let me know in comment. I'll be happy to create a course to cover the hands-on part. Let's quickly go through the topic I'll cover in today's session. I'll start with the basic concept of container, Docker, and what problem it solves. You may be already familiar with Docker and container concepts, but my effort to help associates with different knowledge groups and to bring everyone in the same page, this part is necessary. Then I'll move over to ECS use cases, followed by complete overview of ECS cluster and different ECS cluster components and their interactions. We'll touch base on ECS security aspects. With the principle of least privilege, how can you empower your cluster to have proper access? Then I'll move over to ECS load balancing and dynamic port forwarding concepts. After covering load balancing, I'll focus on ECS service autoscaling, followed by ECS task placement concepts. We will see different task placement strategies and task placement constraints. I'll wrap up the session after covering ECS networking concepts. If you like my effort, please don't forget to like, subscribe, and leave your feedback as comment to this video. Let's get started. What is container? From our day-to-day life experience, and as the image suggests, container is a holder or box to hold multiple small items. We use containers to organize small items in more clean and methodic way. Now, in software development domain, we can apply the same concept to package our applications inside a container that can be run on any operating systems. Applications will run the same way regardless of where they are running. Any machines with a precondition that Docker runtime has to be installed, there will be no compatibility issues, predictable behavior, and easier to maintain, which leads to less work. The next obvious question is how this black magic is possible, and the answer is Docker. What is Docker? Docker is an operating system virtualization technology that allows application to package as container, and Docker is open source, enables you to separate applications from infrastructure. Let's see how Docker containers work on a high level. Let's assume this box as our server where we will run the applications as Docker container. Maybe you have a 3-tier architecture and packaged your UI component, Java component, and DB component in 3 separate containers. When your application will be started, Docker will launch the containers. Now let's assume you are getting heavy load on the processing, or maybe your business logic validation part is getting more and more traffic. What Docker will do? It can automatically add containers to match the application load. Or maybe you are getting more and more UI traffic which does not require any backend processing. Then Docker will scale out your application, adding more and more Node.js containers. Now let's see how Docker works. First, download and install Docker software. If you go to docker.com/get started, you will see different Docker runtimes. Based on the operating system, select the image you want to install. Installation procedures is self-explanatory and just follow the step-by-step process. Next, create Docker file. Again, over internet, you will have standard step-by-step process on how to create Docker file. If you are facing any issues in this step, please let me know. I'll be happy to guide you. When you build the Docker file, it will create Docker image. When you run the Docker image, it will create Docker container. You might be thinking, do I have to repeat the process every time I need a container? The answer is no. The way you manage your application source code and pull or push the code to code repo, the same concept works here too. Docker registry is the place where you can maintain your Docker image. You can push your Docker image to Docker registry. There are different options available. If you want public Docker registry, then Docker Hub is the solution for you. But if your organization requires private Docker registry, then you should consider ECR or Elastic Container Registry. ECS has full integration support with both Docker Hub as well as ECR. Now let's touch base on Docker architecture. Docker uses client-server architecture. Docker architecture has three components: Docker client, Docker host, and Docker registry. Let's start with Docker client. Docker client is the primary interface where any users interact with Docker. When users execute commands such as docker run, docker pull, docker build, the client sends that command to Docker daemon. Docker daemon performs the necessary work for the Docker client. Docker client can communicate with more than one daemon. The next step is Docker host. The main component in Docker host is Docker daemon, or in short Docker D. Docker D listens for Docker API request and manages Docker objects such as containers, networks, and volumes. One Docker daemon can communicate with other Docker daemons to manage Docker services. And the last component is Docker registry. Docker registry is responsible for storing Docker images. The Docker client talks to Docker daemon, which does the heavy lifting of building, running, and distributing your Docker containers. Docker client and Docker daemon can run on the same system, or you can connect to a remote Docker daemon. On a high level, let's understand how different Docker commands work. First, Docker build. So when you initiate that command, Docker client will send that command to Docker daemon. Docker daemon will create a Docker image, or it will build a Docker image from the Docker file. Next is Docker pull. When you execute this command, Docker pull, Docker daemon will pull the Docker image from Docker registry and it will make available for your application to create new container. Next step, Docker run. With Docker run, Docker daemon will create Docker container from the available image. And last but not least, Docker push. If you initiate that command, Docker push, Docker daemon will push the Docker image to Docker registry for further use. Now let's see what are the different container orchestration or management services available. First option is ECS, or Elastic Container Service. ECS is Amazon's own platform, and ECS helps you to run Docker container on EC2 machine. Next option is AWS Fargate. Fargate is Amazon's serverless offering. Serverless doesn't mean that you don't need servers to run your container. You don't have to manage the server or infrastructure. AWS will manage the servers for you. Now, if you have to manage not a single container, but pool of containers, maybe hundreds or 200s container on day-to-day basis, then EKS or Elastic Kubernetes Service is the right option for you. Kubernetes originally developed by Google, but now It's open source container orchestration system for automating application deployment, scaling, and management. EKS is Amazon's managed Kubernetes service, and Amazon will do all the heavy lifting for you. I have created this video only to cover the ECS offering. Now let's see what are the use cases of ECS. The first is microservice. ECS has ability to run multiple Docker container on the same machine. It has easy service discovery feature to enhance communication. ECS has direct integration with load balancer. It also has auto-scaling capabilities. The next use case could be batch processing. You can schedule sequential or parallel batch workload on EC2 or on ECS using AWS batch. You can dynamically provision optimal quantity and type of compute resources. You can schedule ECS containers to run on-demand, reserve, or spot instances. Next use case is cloud migration. You can Dockerize your legacy application running on-prem and then move the Docker containers to run on ECS. Then hybrid deployment. Run the same container both on-prem and cloud. AWS Outpost is fully managed service that extends AWS infrastructure to virtually connect any sites. Now let's see what is ECS cluster and how it works. ECS cluster is logical grouping of EC2 instances. You might be thinking, is this the same EC2 instance you are launching for day-to-day work? The answer is both yes and no. These EC2 instances are built with special AMI, which is specifically built for ECS. And what is the specialty on this AMI? The EC2 instances run ECS agent or Docker container. So the EC2 instances AMI has pre-built ECS agent. At launch, ECS agent registers the instances to ECS cluster. Let's understand the concept with a diagram. In this picture, you can see I have a EC2 instance which has ECS agent pre-installed, and this ECS agent will register the instance to ECS cluster. Now let's see different component of ECS cluster. Let's assume I have 3 EC2 instances with pre-installed ECS agent. This cluster of EC2 instances will create a ECS cluster. So ECS cluster is set of EC2 instances which has pre-installed or pre-built ECS agent. Next is ECS task definition. Task definition is set of metadata written in JSON format to tell the ECS cluster how to run a Docker container. It contains information like image name, port binding for container and host port, memory and CPU requirement of every container, and last but not least, environment variables and networking information. Port binding concept I will elaborate in details in later part of the course. Next is ECS task. When the task definition instantiated, it becomes ECS task. Now let's see ECS service. ECS service helps you to define how many tasks you should run and how they should run. ECS service can link with ALB or NLB for load balancing use cases. ECS service enables you to run and maintain a specific number of tasks or instances run simultaneously in your ECS cluster. In this example, let's say this is a different type of task I am running in this ECS service. On the same time, I can run another set of ECS task container on the same ECS cluster. Next is ECS IAM role. Now this container to work properly, it requires privilege. Now let's see how we can grant privilege to ECS cluster. Let's assume this EC2 instance is part of a ECS cluster, and this EC2 instance has a ECS agent installed. Now in a ECS cluster, ECS agent performs many different tasks, like it has to communicate with ECS service. ECS agent send the container log to CloudWatch. It pulls the Docker image from ECR. Now we have to provide required privileges for ECS agent to work properly. And how can we do that one? We can achieve that using EC2 instance profile. With EC2 instance profile, we can give required privilege to ECS agent such that it can make API call to ECS services. It can send the container log to CloudWatch, and it can pull Docker image from ECR. Now let's assume I have two different containers running to different application tasks, and the containers require different AWS service access to perform its task. Let's assume the first container needs AWS DynamoDB access and second container needs AWS S3 access. Now to use principle of least privilege, I have to provide separate level of access to each container, and to achieve that we can use ECS task role. ECS task role can be created for each task, and it can be assigned separately to that task, such that every ECS task will have required privilege to perform its specific task, and it will not have unnecessary privilege. So with the help of EC2 instance profile and ECS task role, we can equip that ECS cluster or the EC2 instance inside the ECS cluster to perform task as per the requirement. One point to be remembered here, even if the containers run on same system, they don't interact with each other unless we specify. They can scale independently. Let's understand the concept of port binding. When you launch a container inside ECS cluster, container will have two ports, one container port and the second is host port. The mapping between container port to host port is called port mapping or port binding. Now host port will be used to expose the application to outside world. Now when www traffic will come and land to your host port, Docker knows how to route the traffic to the specific container. Now you must be thinking, if the container will scale independently, or if multiple containers of the same application will run simultaneously, how this port mapping work? If I specify the port binding in task definition, will it not create a conflict, or do I have to consider any complex logic in task definition? To resolve this issue, ECS supports dynamic port mapping. That means you will specify the container port at task definition, and the host port will be assigned at runtime during the container launch. In this example, let's say I have a ECS cluster where I have two EC2 instances, and I have launched the Apache cluster or Apache container 4 times. And as you can see, I have different host port based on their launch sequence, right? Now you might be thinking how my application or how the traffic from outside world will be navigated to these containers, or how I'll manage the traffic. To answer this question, AWS Application Load Balancer has the perfect solution for you. and that is called dynamic port forwarding. So AWS Application Load Balancer, it can forward the traffic to dynamic port, and with that dynamic port forwarding, you can scale independently and you don't have to manage that port binding or static port binding feature, or here you are overcoming the limitations of static port binding. Now let's see what are the use cases. You can increase resilience even if the application is running on a single EC2 instance. With this, you can maximize utilization of underlying resources, that means CPU or RAM. You have the ability to perform rolling updates without impacting application uptime. With rolling updates, it means you will run two different versions of your application, one recent and one older version, and you can distribute traffic based on a weight. Maybe 10% of the traffic will go to your new instance and 90% of the traffic it will go to your old instance. And when you feel that your new instance or new launch is perfect, then you can route all the traffic, or you can put 100% traffic to the new instance and discard the old instance. Now we can launch multiple containers of the same application simultaneously. Next question would be how we can automatically scale out based on loads. ECS service autoscaling is the answer for you. CPU and RAM is tracked in CloudWatch at ECS service level. You can utilize this matrix to scale your ECS service as per requirement. There are different scaling strategies available and you can select any one. Let me start with target tracking. Under target tracking, scaling is based on a specific targeted average CPU or RAM metric in CloudWatch. For example, you can specify a scaling technique like if your CPU utilization is greater than 70%, add a new task container. Next is step scaling. Step scaling, here you can specify multiple thresholds along with different responses. For an example, let's say you have created three thresholds. Threshold A, where you specify add one instance when CPU utilization is between 40% and 50%. Then your next threshold could be add two instances when CPU utilization is between 50% and 70%. And the last threshold you have created where you have specified that add three instances when CPU utilization is between 70% and 90%. And the next scaling strategy is schedule scaling, where you can scale based on a predictable change or based on a predictable schedule. Now you might be thinking these scaling strategies are very similar and you already use this strategy in EC2 autoscaling. So whether EC2 autoscaling and ECS service autoscaling is same? The answer is these scaling techniques are same. But ECS service autoscaling, that means at task level, is not equal to EC2 autoscaling at instance level. Now to explain this feature with the help of a diagram, let's consider I have a ECS cluster with two EC2 instances and my cluster is running with 4 Apache tasks, and there is a scaling strategy that if CPU utilization is more than 70%, then launch one more cluster. But if you see the diagram, there is no more space available for a new task. So EC2 autoscaling, it will try to launch a new task container, but there is no space in the underlying host such that it can place that task. So if you now understand, ECS service autoscaling will only increase or decrease, or it will only scale out or scale in your task container, but it will not take care the EC2 instance level autoscaling. That means it will not create the underlying hardware to place your ECS task. Now, what is the solution for that one? There are two solutions available. Either you can go to forget autoscaling As I told earlier, Fargate is serverless offering. That means here you don't have to provision any underlying hardware or EC2 instances. Service autoscaling with Fargate is a great combination, and you don't have to really consider about any EC2 instances. And the next option is ECS Cluster Capacity Provider. To autoscale ECS service and EC2 both together, you should define ECS Cluster Capacity Provider. Now let's see what is ECS Cluster Capacity Provider. Amazon ECS Cluster Capacity Provider are used to manage the infrastructure in which your ECS tasks run. Each cluster can have one or more capacity providers and an optional default capacity provider strategy. The capacity provider strategy determines how the tasks are spaced across the cluster's capacity provider. When you run a standalone task or create a service, you may either use the cluster default capacity provider strategy or specify a capacity provider strategy that overrides the cluster default strategy. This allows your capacity provider to automatically provision infrastructure for you. So on short, cluster capacity provider will allow you to take care underlying EC2 host. That means if you do not have, or if your current ECS cluster is running out of space, cluster capacity provider will launch a new EC2 instance and it will place the job in new instance. Now there are two types of cluster capacity provider. First, ECS on Fargate. In this case, AWS will automatically add Fargate and Fargate spot capacity providers. So you really don't have to do anything. For ECS on EC2, here you as a user to associate the capacity provider with an autoscaling strategy. Now, if I'll go back to my previous example, we saw when my CPU utilization was more than 70%, as per the scaling strategy, there should be one new task, but in my current cluster, there was no provision to place this task. Now, if I have ECS cluster capacity provider, what it will do? It will launch a new instance and it will place the task on that new instance. Now, let's explore ECS task placement. One thing to be remembered here, this is applicable only to ECS on EC2. As in Fargate mode, you are not maintaining the underlying hardware, you can't control the task placement. When a new task is launched, ECS on EC2 must determine where to place it. On the other hand, when a service scales in, ECS needs to determine which task to terminate. ECS task placement can be controlled using task placement strategy and task placement constant. Let's explore them in detail. First, ECS task placement strategy. There are main three strategies. Let's start with binpack. Binpack is based on least available CPU or memory. What it will do? It will first fill your EC2 instance with tasks unless and until there is available memory. When there is no more space or no resources available, then it will create a new instance and it will place the task on the new instance. So now you can understand this is most cost saving option. If I'll try to explain that with animation, so first it will compact all the tasks in EC2 instance. When there is no more space, it will launch a new instance to place the incoming task. Next is random. As the name suggests, it will place the task on any EC2 instance randomly. This is the most simplest placement strategy. If I'll try to explain with the help of animation, the task placement strategy looks like this. Third strategy is spread. Under this strategy, tasks are placed evenly based on the specified value. Accepted values are instance ID or any platform or custom attribute that is applied to a container instance, such as ECS availability zone. In this example, I'll try to use availability zone as my value, and I'll try to explain how a spread strategy will work if availability zone has been considered for this strategy. Now if you see, task will be placed evenly based on the availability zone. As the example suggests, this is ideal for fault tolerant. Now there could be another strategies where you can mix and match this strategy and create hybrid strategy, and you can create your own. Now let's explore ECS task placement constants. A task placement constant is the rule that is considered during task placement. Task placement constant can be specified either when running a task or creating a new service. The task placement constant can be updated for existing service as well. There are two task constants you can apply to your service. The first one is distinct instance. Under this constant, ECS will place each task on different container instance. This placement constant can be specified when either running a task or creating a new service. Next, you can use member of constant. Under this constant, ECS will place tasks on container instances that satisfy an expression. You can use cluster query language to create the expression. As an example, you can define place the task only if instance type is T2 micro. The member of task placement constant can be specified with actions like running a task, creating a new service, creating a new task definition, and creating a new revision of existing task definition. Since we explored the task placement and task placement constant, now let's explore how ECS places the task, or ECS task placement process. First, ECS will identify the instance that satisfy CPU, memory, and port requirements. Once that is done, ECS will identify the instance that satisfy task placement constants. Then ECS will identify the instance that satisfy task placement strategies. When all the three rules satisfied, ECS will place the task on that instance. Now let's explore ECS task networking. As you have already learned, you can host ECS either on EC2 instance or in Fargate. We'll explore the networking options for both the modes. Let's start with ECS task hosted on EC2 instance. The networking behavior of ECS task hosted on EC2 instance is dependent on the network mode defined in the task definition. And there are 4 different types of network mode you can define. First, AWS VPC. Under this mode, each task allocated its own elastic network interface, or ENI. Each task allocated its own primary IPv4 address. As a result, each ECS task or each ECS container will have same networking capability as EC2 instance. Next is bridge mode. The task utilizes Docker's built-in virtual network, which runs inside each Amazon EC2 instance hosting the task. The third option is host. Under this strategy, the task bypasses Docker's built-in virtual network and maps container port directly to ENI of the Amazon EC2 instance hosting the task. As a result, you can't run multiple copies of the same task on a single EC2 instance when port mappings are used. And the fourth option is none. The task has no networking connectivity under this option. Now let's move ECS task hosted on Fargate. Here the default mode is AWS VPC, and if you have dual stack mode enabled, each task will have IPv4 and IPv6 address together. One thing to be remembered here, one task can have only one ENI associated at a time. You can't attach multiple ENI with one task. With this, I'll conclude today's session. Thank you very much for your support. If you like my effort, please like, subscribe and share this video. Please don't forget to post your feedback in comment. Thank you again. Stay safe. Take care.